This video is about statistics, random number generation, and formulating models, but I want it to be as accessible as possible, so verbally I will try to keep things simple, and I will add more detailed remarks as text. For those interested in history and world building, but not so much in the math, look to my summaries at the end of the video chapters. At the timestamps, look to the screen. Goblins are mythological creatures that are all over fantasy fiction. They're characterized as short humanoids, but are they all equally short? If they're anything like humans, most of them would be around average height, whatever average is for them, say 120 centimeters or 4 feet, and there would be a small number significantly taller and significantly shorter than average. Mathematically, their heights would be on a bell curve, what is called the normal distribution. The range of possible heights is on the x-axis, and the y-axis gives the value of the probability density function, a measure of how likely a goblin is to be of the corresponding height. At 125 centimeters, the curve is quite high. Still fairly high by 130 centimeters, but for 140 centimeters it drops off. One way to think of this is to imagine going to a courtyard of a goblin fortress, or wherever a bunch of them hang out, and to mark out a bunch of boxes on the ground, say for example 20 different rectangles. The goblins would then go and stand in the boxes by height. So the first box is for heights between 100 and 102 centimeters, the next one from 102 to 104 centimeters, and so on. These boxes are called bins in the statistical sense. Suppose that you wanted to randomly generate a band of 100 goblins for a game, and wanted their heights to be spread realistically. With 20 bins defined, each one 2 centimeters wide, you could roll a 20-sided die to select a height for each goblin. If you roll a 1, the goblin has a height in the first bin, and so on. The problem with this approach is that a fair die is just as likely to land on a 1 as it is on 10. It's therefore just as likely that a given goblin is really tall as he is to be of average height. But, as we've said, the average is much more likely. In other words, a die produces a flat, uniform probability distribution, while heights are meant to be normally distributed. This is the case for a game on a computer as well. There are algorithms to quickly generate random numbers, but they're also uniform. Each number is equally likely to come up. What's needed here is to take such a uniform distribution, which looks like a flat line on a graph, and to map it into an arbitrary probability density function like the normal distribution, the one that has a bell curve, or different ones we'll see in a bit. Going back to Victorian times, there were attempts to do this mechanically, basically to use the physics of random processes to effectively generate random numbers. One example is the Galton board, which uses small ball bearings bouncing around randomly. It's a little bit reminiscent of one of those arcade coin pushers or a pachinko arcade machine. Each of the little balls bounces until it falls into a bin, with the probability roughly following a bell curve. The problem with using the Galton board is that it's not very practical to have a mechanical tool just for random number generation. But more importantly, the physics limits the probability distribution that will be obtained. It's fine for getting a bell curve, but what if we wanted a radically different curve? On the other hand, the idea of one of those coin drop machines does provide a hint at how to solve this problem. Using a 20-sided die was a bit like taking a ball and dropping it randomly into one of 20 chutes going straight down until it falls into a bin. But it's possible to make the chutes diagonal, so the ones in the middle would narrow down into very thin bins, while the ones on the edges would expand outwards. In terms of our picture of goblins in the castle courtyard, this is like redrawing the boxes on the ground so that there are equal numbers of goblins in each box. Yes, extremely short heights are less probable, but because the size of the box is larger, there's a larger range of those shorter heights grouped together, and it evens out. Now, using a 20-sided die to randomly assign a height from these new bins is just fine, because we've constructed the bins in such a way that a goblin is equally likely to occupy every one of them. What we need then, mathematically, is a way to split the bins in such a way that the corresponding probability of each one is equal. To do this, we need the cumulative distribution function, which has its own curve. For each goblin height on the x-axis, it's no longer about the probability of being around exactly that height, but instead it gives the probability of being at that height or any possible height below. At 10 centimeters, it has a value of 0, because there is simply no chance that a goblin is a minuscule 10 centimeters tall or even shorter. 120 centimeters, remember, is the average height, so exactly half of the goblins are below it. The cumulative distribution function takes a value of 1/2. At 1000 centimeters, the curve has a value of 1, because every goblin is certain to be below a height of 10 meters. The curve rises between these points. Every possible probability density function has its own corresponding cumulative distribution, and if you know calculus, it's straightforward to go from one to the other. In some cases, it may not be possible to do this analytically with a pen and paper, but one way or another it can be done numerically on a computer. Once we have the cumulative distribution, we can get to work. Suppose that, as before, we want 20 bins. Each one must now have an equal probability, so 1/20 or 5%. In other words, if we had a large number of goblins in the castle courtyard, we want 5% of them to go into a particular bin based on their height. Remember what the cumulative distribution represents. There's a particular height that 5% of the goblins are at or below. That sets the upper edge of the first bin. There's another height at or below which 10% of the goblins are. From that height down to the top of the first bin is another 5%, and so on and so forth. So effectively, we can go up the y-axis in steps of 0.05, then go across to the curve and down to the corresponding height on the x-axis. This gives the upper edge of one bin and the lower edge of the next bin. If I draw the bins for the distribution of goblin heights, you can see that the bin sizes are large on the edges, where the probability of having an extreme height is lower, and the sizes are small in the middle, where being of average height is more probable. What's needed then is the inverse function of that cumulative distribution. It takes a given probability and returns, in this case, a height. So if the cumulative distribution is known, an inverse function can be calculated, and then evenly spaced probabilities are the inputs, while the boundaries of the bins are the outputs. Finding the inverse of a given function is not always possible analytically, but luckily I heard there's already a good video out there about Brent's algorithm, a way to find the inverse of any function numerically. With a 20-sided die, you're limited to having 20 bins. It's much easier to just use a computer, which can easily generate a random number from 1 to 1,000,000 or more, and do the legwork of assigning the bins. Starting with any arbitrary function, it can be integrated numerically to normalize it and generate a cumulative function, and then invert it by Brent's method to create a random number generator. Together, this gives a straightforward method for randomly generating numbers which are distributed according to any curve that you could possibly invent. Even if you're not too familiar with statistics, hopefully this section has explained the idea of binning together certain random outcomes. It may be goblins of similar heights, days with a given amount of rainfall, and so on. Then there would be some probability distribution determining how likely that outcome is. A goblin is more likely to be of average height than really tall. A rainforest is more likely to have a day with lots of rainfall rather than be dry. Finally, even if you're not too concerned about the details, hopefully I've convinced you that there is a way to randomly generate these outcomes based on a probability density function linked to that type of outcome. And now I'd like to talk about medieval urbanism. Just as every goblin has an associated number for their height, a settlement has associated with it the number of residents inside it. A settlement with 50 residents is a village, whereas one with thousands is a city. Settlements can be binned together based on the number of residents, and a probability distribution can be determined for how those bins ought to be filled. I'm going to once again use the Domesday Book as a dataset. This was a survey of England conducted in the year 1086 by the Normans, who had taken over the country under William the Conqueror. The Normans became the new landed aristocracy, immediately wanting to tax their subjects, and for this reason they recorded an account of what could be taxed. A team at the University of Hull has painstakingly translated and digitized the records, and, where possible, has matched each entry to modern-day coordinates. Their work has kindly allowed me to make this analysis. For most settlements in the country, the Normans recorded the number of people living there, as well as the numbers of ploughs, cattle, mills, and so on. This sounds perfect for the problem I've described. Let's just take the dataset and get binning. There are a few problems, however. First of all, the entries don't correspond to an individual person, but to a household. One villager in the book might be a widow living on her own, or a household with an extended family. As a simplification, I'm therefore applying a flat multiplier of 4 real humans for every person mentioned. Secondly, the Normans took over as the feudal ruling class, which had land and estates in the countryside, but not generally in cities. The cities and boroughs had their own administration and would simply pay a tax to the aristocrats. For example, before the Norman invasion, every year the city of Gloucester paid £36 to the king, but also provided 100 drawn iron rods for nails for the king's ships. After the conquest, the city would pay £60. This arrangement means that the records for cities are much less detailed, because the king and the dukes didn't care how many people lived in a given city as long as they got paid. Thirdly, on that note, while the digitized version of the Domesday Book has neat database columns and rows, the Normans working with quills and parchment weren't so systematic. For the countryside, it's not so bad. The residents are broken down into villages, smallholders, and other social groups. The urban centres are much more of a mess. The city of Southampton lists, specifically, 65 Frenchmen and 31 Englishmen, besides a number of unspecified other men and houses. The city of Canterbury lists 231 burgesses. In this case, a burgess is just a citizen of a town. It's not clear how many of those were Frenchmen or Englishmen, so the data is uneven. What I've done then is to sum up all the people mentioned in the small settlement records and multiply them by 4. Then to sum up all the burgesses, merchants, houses, and messuages in the large settlements and multiply them by 4 as well. Then it's just a matter of binning them, which I have chosen here to be 100 in size. Namely, the first bin contains villages between 1 and 100 residents, the next bin from 101 to 200 people, and so on. On this chart, what's clear is just how many more small villages there are compared to larger towns. The bar for the first bin towers over the others. Going from the first bin to the second drops the number of villages by almost a factor of 3, then down by a factor of near enough 3 to the next bin and the next one. In fact, let me make the y-axis logarithmic in scale. That means that every division goes up by a factor of 10. A scale like this allows the pattern of how the settlement sizes are distributed to be seen more clearly. Certainly, it is no bell curve. I want to stress that between the Normans recording it, the University of Hull digitizing it, and myself analyzing it, there are gaps and errors. It's likely that this is an undercount, particularly in the cities, but let's take it as it is for now. Also, just to note, there are entries which have precisely 0 people. Some of them are cities that I'll come back to in a moment. Some have been deliberately destroyed by the Normans, and in some the records only list things like mills or churches but not people. I've excluded them, so that the lowest bin begins at 1 person. The next thing to consider is just what constitutes a city. At what size does a settlement go from village or town to city? The Normans themselves had some feelings about this. The word city comes from the Latin civitas, which is used in the Domesday Book. Shrewsbury, or Sciropesbury, as it should be pronounced correctly, had 252 recorded houses in 1066 and is referred to as civitas. After adding up all the entries and multiplying by 4, I count 1,116 total people. Looking at the chart, there is a small bump in the bin between 901 and 1,000 inhabitants. I therefore take 900 as the threshold above which a town becomes a city. With that definition and the approximations I have made, there are 41 settlements in the Domesday Book which satisfy the population requirement to be a city. There are at least 8 more that are mentioned in the Domesday as a city, and we know from other sources, archaeology and so on, that they were in fact cities, but for which we don't have accurate numbers. These include London and Winchester. Let's set these aside for now. I'll break up the chart into the part with the villages and the part with the cities and try to fit a curve to each of them, then join them up in the end. When taken as a probability density, the villages look like they lie almost on a straight line, but with a slight curve to it, so I take that to be roughly quadratic. When moving back from a logarithmic scale to a linear one, as required to make a probability density function, that would mean a curve of the form 10 to the power of ax squared plus bx plus c, where the constants are determined by a fitting routine. The cities are a bit more tricky. Because there's so little data, there are very few cities in medieval England, relatively speaking, it becomes difficult to get meaningful statistics out. At 100 people in size, most bins are empty. So for example, there are no cities between 6,000 and 6,100 inhabitants. What I've done therefore is to merge some of these small bins into larger ones. I have the bin edges go from 1,000 to 1,300 to 1,700 and in a single bin all the way up to 8,200. Taken like this, it's still a bit noisy, but with a logarithmic scale I'm going to shut my eyes and pretend that this is roughly a straight line, meaning that the probability distribution is exponentially decaying. Now let's bring back those 8 cities for which we don't have population numbers. I'm going to assume that they are distributed like the others, that they fall on the same curve. What that does then is to raise this part of the curve here. Next, I've brought the two parts together to form a single probability distribution function. They're ever so slightly mismatched around where they join at 900 residents, so there's a jump. Now that's not a problem, this function need not be continuous as long as it's integrable, but since this is approximate anyway, I feel there's no harm in shifting the city portion up a little bit just to actually make the function continuous. This does increase the proportion of cities somewhat, but not by a huge amount. Finally, it can be normalized so that the total probability of getting any result is exactly 1. Now this is a perfectly plausible probability density function, with the parameters given on the screen. I'm going to call this the excavator bucket distribution, with the curve for the villages looking like the bucket itself, and the cities, part of the curve, looking like the teeth. I will just note that this is not a perfect fit to the data, so it doesn't reproduce the Domesday dataset perfectly, as we'll see in a moment. That was a lot of statistics, but let's take a step back and take stock. Previously, as an example, we had a curve which gave a measure of the probability that a given goblin would be so many centimeters in height. And then we used that curve to make a random number generator which could be used to create goblins with correctly proportioned heights. Now we have a new curve. It looks very different, but it serves a similar purpose. If you were to pick a settlement in England in 1086 at random, this is a measure of the probability that the settlement would have a certain number of residents. That curve starts relatively high and drops off very quickly, meaning that if you picked any settlement, the overwhelming likelihood is that it would be a small village with very few people living in it. But there is a chance that it could be a town or a large city. We can, of course, use this data to extrapolate from the real world to a counterfactual or entirely fictional one. And I think that there are 3 ways to do this in increasing complexity. The first is to simply scale up the numbers of settlements by some constant factor. Suppose that there is some fictional territory that is statistically identical to medieval England, but simply has double the territory and double the population. England, we noted, had 49 cities, once we added in the ones with missing data. So our fictional country should have twice as many, 98. Then also double the number of villages and towns. Let's take Tolkien's Middle-earth as a fictional example and try to estimate the number of cities it would have with the Domesday Book, at least as a starting point. Let's suppose that between Gondor, Rohan and the Shire, there are very roughly 5 Englands. Let's ignore the orcs, dwarves and wood elves, who have radically different economic and social structures, and so that would correspond to 245 cities in total. The second thing we could do is to use this probability distribution to randomly generate settlements until some total population is reached. For example, let's say that a fictional country had 2 million inhabitants. Then, randomly generate numbers from the excavator bucket distribution. The first one might be a village of 35 people, then a town of 204, and so on. Stop when that total reaches 2 million, and you have a long list of every single settlement in the country by number of inhabitants. To apply this method to Middle-earth, we would first need an estimate of its total population. I'm only going to look at Rohan and Gondor, and I'm going to estimate their populations by comparing their land area to that of England. England's borders have changed over time, so I'm going to take the area to be roughly 50,000 square miles. In my version of the Domesday dataset, its population is about 1,120,000. Taking a publicly available map of Middle-earth and drawing polygons around Gondor and Rohan, I get their areas to be about 140,000 and 90,000 square miles respectively. However, I assume that Gondor has a slightly lower population density overall, say 90% of England, because its territory includes mountains and other sparsely populated zones. And Rohan has a much lower population density, just half as many living per square mile as England, because with its horse lords, its society is much more rural. This rough estimate gives a total population of 3,765,000. I was then able to randomly generate settlements distributed similarly to the Domesday Book until I reached this population number, building up a hypothetical dataset of settlements. When I binned the settlements as I did before, this is the graph I got. As I mentioned, however, my fit was not perfect. We would expect about 160 cities from a simple scaling up of the Domesday data, but I get 256 from the random number generator. Furthermore, there are 12 large cities above 4,000 inhabitants in size, compared to 9 or 10 that would have been expected from simply scaling up the Domesday data. I actually think this fits the setting a bit better, with there being larger Gondorian cities like Minas Tirith. Again, that's just because the excavator bucket doesn't quite fit the real data precisely, but it's close enough. The third thing we could do is to take this probability distribution and get a bit creative with it. As I've said, the sharp drop of the bucket part of the curve implies that there are many more small villages as opposed to large villages or towns. A more urbanized society, then, would start off lower and drop off in a shallower manner. There would be a decrease in smaller settlements and an increase in larger ones, relative to England as it was in the Domesday Book. This might happen if the country were more densely populated. If you try to cram more people into the same amount of land, they would have to coalesce together into larger and larger settlements. On the flip side, if there were a more rural society, a more sparsely populated territory, then the curve would start even higher and drop even sharper. In terms of Middle-earth, I would hazard a guess that Gondor would be more urbanized than England in 1086, while Rohan would be slightly less, and the Shire much less so. I actually think that the Shire's distribution would drop so rapidly that it would hit 0 before reaching 900, meaning that there is 0 probability of any settlement having a population greater than 900, and therefore no cities, and that's why I excluded the Shire from the last part. In fact, these sorts of statistical differences aren't just important when comparing two neighboring countries, but when looking at the development of a given country over time. As the Middle Ages gave way to the early modern period, England's population would have grown and it would have urbanized more. The probability distribution curve would have become shallower. The bubonic plague depopulated it again, and the curve would have regressed somewhat. Tolkien's Middle-earth has a deep lore, and the same sort of processes would also have taken place. I'm going to imagine the situation at just one point in its history. I'm going to keep the population numbers from before. Gondor at nearly 3 million, Rohan at just shy of 1 million. Relative to Domesday, I've chosen a gentler and therefore more urban distribution for Gondor, at the same time as a steeper and therefore more rural distribution for Rohan. I'm assuming that for every other society in Middle-earth, the distribution, whatever it is, drops to 0 before reaching 900 inhabitants. This means that however many settlements there are outside Rohan and Gondor, precisely none of them are cities. Running the random number generator, I get 435 cities in Gondor and just 30 in Rohan, so 465 cities total in Middle-earth at this time. So there we go. Having looked at what a probability density function is in general, we obtained one based on the Domesday Book, and then used that as a model to inform us about the number of villages, towns, and cities in the fictional world of Middle-earth. By estimating it in different ways, I get, about 350 cities in size over 900 inhabitants. I'm sorry to disappoint you if you were coming for a deep dive into the lore of Gilraen, daughter of Ivorwen, and so on, but truthfully, I'm not a huge Tolkien fan. I think that while Tolkien did a great job with the languages and customs, he seemed to pay a lot less attention to the economics and demography of Middle-earth, which to me, personally, is more interesting. That's why I started with medieval England, which I think is a reasonable model for other pre-industrial societies as depicted in The Lord of the Rings. If you're working on your own fictional world, I would strongly urge you to at least think about these kinds of statistics. If you're a writer, get in touch with me or any mathematics-related graduate if you want to talk about this sort of thing in more depth. The math can be involved but doable. Note as well that just because this kind of analysis doesn't make sense within the context of the world you're imagining, whether historical or fictional, doesn't mean that you cannot do it as a writer or historian. Yes, Rohan, as depicted in The Lord of the Rings, might not have the administrative and technical capacity to conduct a survey of its settlements, but that doesn't stop us from being able to think about it. I hope you learned something, and thank you for watching.